It's very useful to understand how the poles and zeros of a system described by a linear constant coefficient difference equation impact the frequency response magnitude. So basically, we want to study how the poles and zeros influence the magnitude of h of e to the j omega. We know that if our system is stable, then the region of convergence is going to include the magnitude z equals 1, or the unit circle, so I can obtain the frequency response magnitude from the z transform by substituting for z with e to the j omega. So my frequency response for a system described by a linear constant coefficient difference equation is just the sum k equals 0 to m bk e to the minus j omega k divided by the sum k equals 0 to n ak e to the minus j omega k. Now it's useful to rewrite this in pole zero form, as we have done previously on other occasions. We'll write h of e to the j omega as b0 over a0, factoring out the coefficients of the constant term in the numerator and the denominator. And then we'll be left with a product of terms that have zeros and poles in them. So we'll have from k equals 0 to m of 1 minus ck e to the minus j omega. And then we'll have from k equals 0 to n, 1 minus dk e to the minus j omega. So if I take the magnitude of this expression, the magnitude of a product is just the product of the magnitudes. So I can write this as the magnitude of b0 divided by the magnitude of a0. The product, 0 to m, of the magnitude of 1 minus ck e to the minus j omega times the product k equals 0 to n of 1 minus dk e to the minus j omega. Now what we're going to do is factor e to the minus j omega out of the numerator as well as factor it out of the denominator terms. And if I do that, I'm not going to have e to the minus j omega on the ck, but I'm going to end up with e to the plus j omega in place of the 1. And I have the product, k equals 0 to m, of the magnitude of e to the j omega minus ck divided by the product k equals 0 to n, magnitude of e to the j omega minus dk. The term that we factored out, the e to the minus j omega, from each of these m products, of course, has magnitude 1, as does the e to the minus j omegas that we factored out of the denominator. So this term doesn't have an impact on the magnitude. Now, this is a very useful form in which to study the relationship between the frequency response and the poles and zeros of the system. What we see is that the magnitude of the frequency response depends on terms of this type. In the numerator, we had e to the j omega minus a 0, and in the denominator, we had e to the j omega minus a pole. So if we understand how this term behaves, we can characterize the entire magnitude response of the system. What we're looking at is a vector connecting the point e to the j omega, which lies on the unit circle. So this has unit magnitude and angle omega. So this point right here is e to the j omega. And then I have some other point a, and e to the j omega minus a is a vector connecting e to the j omega to a. And when we take the magnitude of that, we're looking at the length of this vector. That's what we're using in our frequency response magnitude. So if I write that out again, I've got this constant term out front, magnitude of b0 divided by the magnitude of a0. And then in the numerator, I've got a product of terms that are the distances from e to the j omega to the 0 locations. And then in the denominator, I've got a product of terms representing the distances from e to the j omega to the pole locations. So we can think about the magnitude response of our system as the product of the distance from e to the j omega to the zeros divided by the products of the distances from e to the j omega to the poles. Now it turns out that if e to the j omega is close to a 0, then the distance between e to the j omega and the 0 is very small, and since this is in the numerator, it's going to make h of e to the j omega small. On the other hand, when e to the j omega is close to a pole, Then, again, this distance between e to the j omega and the pole becomes small, but that distance shows up in the denominator. So as this distance becomes close to 0, it causes h of e to the j omega, the magnitude, to become large. So let's take an example where I have h of z as 1 minus 3/4 z inverse in the denominator and 1 in the numerator. So this particular system has a 0 at z equals 0 and a pole at z equals 3/4, as we've shown in the pole 0 plot on the bottom. Well, if I pick my frequency omega 1 fairly close to 0, or the z equals 1 point, then the distance from the 0 to e to the j omega 1 is Lz, and that's going to be 1. But the distance from the pole, which we're denoting as Lp, to e to the j omega 1 is going to be close to 1/4, because this is at 3/4, so this is at 1, that means this distance is 1/4. So when I compute the magnitude of h of e to the j omega 1, it should be approximately 1 divided by 1/4, or 4. And indeed, that's exactly what we obtain. Changing the frequency a little bit, moving further around the unit circle, now if I pick a frequency near here for omega 2, well, Lz, the distance to the 0, is going to stay at 1, but Lp, the distance to the pole, is now gotten quite a bit bigger. And let's suppose that that's about 0.77, in which case magnitude of h of e to the j omega 2 is approximately 1 over 0.77, which is approximately 1.3. And if we pick a frequency here of omega 2 that is somewhere in that vicinity, we see that indeed we're getting about that value. Continuing, moving the frequency further, now out here at omega 3, we've got again the distance to the 0 is 1. The distance to the pole has gotten further, now it exceeds 1, and we'll suppose that it's about 1.25, in which case h of e to the j omega 3 magnitude is approximately 1 over 1.25, or about 0.8, and that's indeed what you see for omega 3, a little bigger than pi over 2 radians. And finally, as we get near omega equals pi, at say omega 4 here, again the distance to the 0 remains at 1, but the distance to the pole starts to approach 7/4, and consequently the magnitude of h of e to the j omega 4 becomes approximately 4/7 as we get close to pi. By studying the distances from the unit circle to the poles and zeros, as we vary frequency from 0 to pi, we can gain a lot of insight into the nature of the frequency response magnitude of the system. Here's a second example where I have a second order system. I have two zeros, one at z equals +1 and the other at z equals -1. And then I put two poles very close to the unit circle at 0.95 e to the j pi over 4. So what we're going to have for our frequency response magnitude is the product of the distances to each zero, Lz1 and Lz2, to a particular point on the unit circle associated with a frequency, say omega 1. In the denominator, we'll have the product of the distances to each of the poles, LP1 and LP2. So as we vary omega 1 around the unit circle, this distances all change and our frequency response magnitude consequently changes. And what you can see right away is that when omega 1 is equal to 0, then we have a 0 right on the unit circle, and we know that the frequency response, well, the distance Lz1 goes to 0, so the magnitude of h of e to the j omega 1 has to be 0, and indeed we see that when we plot the magnitude response. Another interesting thing happens when we get omega 1 real close to the pole. In that case, the minimum distance between the pole and omega 1 on the unit circle becomes 0.05 when omega 1 is pi over 4, because the radius of this pole is at 0.95. Consequently, in the denominator, I have a fairly small number, and these other factors are all much bigger. When I multiply these terms and I divide by the small number LP1, I get a value that's quite large. So I'm going to have a peak in the frequency response magnitude here as I pass by real close to this pole, because LP1 shrinks to a very small number. And then as I get farther away again, the distances change, and I don't have anything small in the numerator or the denominator, so my response falls off. And then once I get over here near this 0 again, the distance LZ2 is small, where the distances LZ1 and LP1 and LP2 are fairly large. So again, our frequency response goes to 0 as omega 1 approaches pi. Basically, what's happening here is that when you have a pole near the unit circle, you push the magnitude response up at those frequencies, while zeros near the unit circle pull the magnitude response down. And if the 0 is on the unit circle, of course, then it forces the magnitude response to be exactly 0. Now, this kind of insight can help us understand the characteristics of filters from looking at their pole zero plots. We can also use these ideas to design filters. So if I want a filter that attenuates a certain frequency, what I need to do is put a 0 on the unit circle at that frequency. Let's look at an example here where I've got a filter with 8 poles, and they're arranged in sort of a semicircle about the z equals j. And then I have zeros at 4 of them at z equals 1 and 4 zeros at z equals minus 1. So what can I learn from this? Of course, I know what happens here is that my frequency response is going to be 0 at omega equals 0 and omega equals pi because of these zeros. And so as I go along the unit circle, I'm getting closer to these poles. Those show up in the denominator. As those distances shrink, it's going to push my response up. So I'm going to predict that I have sort of a pass band in this frequency range here, and then it drops off again. So this is going to be, I predict this is a band pass filter. I start with a gain of 0. I get a higher gain in this region, and then my gain drops off to 0 again. And if we look at the actual frequency response magnitude, we see that indeed about the frequency pi over 2, I have my passband, just as we predicted from our pole locations here. And that at 0, we've got 0, and at pi, we also have 0 because of these zeros. So from looking at the pole zero plot, I can infer what the frequency response characteristics are going to be. Take another example. In this case, we have 20 zeros distributed throughout the z-plane, and all 20 poles are at the origin. So poles or zeros at the origin don't affect the frequency response magnitude at all, because the distance to the unit circle to the origin is always 1. So in this case, the zeros are going to entirely define the behavior of the system. And I know that these zeros on the unit circle are going to cause me to have frequency response magnitude 0 exactly at those frequencies. But in general, I can write then my magnitude response as product B0 times I equals 1 to 20, the product of L sub I, where L sub I is the distance from the point on the unit circle corresponding to omega to each of the zeros. So we're going to have 20 distances here. We don't have to worry about the poles because those are all the same. And what you can see is that in this region, the distances to the zeros are all larger numbers. We're not close to any particular zero. So I would expect that I have higher gain in this region than I do at the very high frequencies near pi or the lower frequencies below pi over 2. So in this case, I'm going to predict that I have another bandpass system where from 0 to somewhat greater than pi over 2, I have very small gain. Then I have a passband in this region, and as I get near pi, it should go back to 0. And indeed, we see that as we get a little bit bigger than pi over 2, this region here, we start to have a passband, and then we have our passband ends out here as we start to get a little bigger than 3/4 pi, and we have stop bands or attenuation between 0 and certainly pi over 2, where this 0 is, and then at the very high frequencies as well. So there's a lot of intuition that can be gained by understanding how the poles and zeros affect the frequency response magnitude. You can also study how the poles and zeros affect the frequency response phase, but the analysis is quite a bit more complicated and consequently not as insightful.